In this video, we're going to look at Chapter 10, Section C, on three-dimensional problem solving. If we take a look around us, we see that right-angled triangles occur frequently in three-dimensional figures. For example, we see right triangles in buildings, there's a right triangle there. We can use right triangles to help us find the height of trees. If I can view the angle of elevation, which we've seen in previous chapters, I can use right triangles in trigonometry to help me find the height of a tree. Also, right triangles are used frequently by satellites, who are constantly helping us find our location. In our GPS devices, our cell phones, and for the government, these are very important. So we see trigonometry and right triangles in a lot of different places. One of the key tools that we have to remember to use when we're solving problems in three-dimensional space is the Pythagorean theorem, which again states that a squared plus b squared equals c squared. C squared, or c, often being the hypotenuse. We can also use our trigonometric ratios and their inverses of sine, cosine, and tangent. In three-dimensional objects, such as boxes, like the figure that's shown here, we often talk about shadow lines or projections. And a shadow line or projection is the shadow cast by a diagonal and in this case, we'll use the example AG. That is projected on the base plane. And in this example, the base plane is EFG. EFGH is the base plane. And we don't need brackets because we're representing the plane, not a line. And so if I were to shine a light directly down on the top of this wire-framed cube, and we had a wire connecting the points A and G, it would cast a shadow directly underneath it on the line EG. So in this case, EG is the projection of the line AG on the base plane EFGH. You can see what I've done is I've created some right triangled figures with inside the wire frame. And using trigonometry, I can find specific angles between the wire and its projection, or the wire and the base. And this brings me to the next topic that we're going to cover in this section, which is that the angle between a line and a plane is the angle between the line and its projection on that plane. So if I can find the angle between a line and its projection, I automatically know the angle between the line and the base plane. Hopefully this will become more clear as we work through a couple of examples. In the first example, I'm given a basic cube shape, and I want to find the angle between the diagonal AB. So let's draw that diagonal. Try to picture this in three-dimensional space. I want to find the angle between AB and one of the edges at B. Now, it actually doesn't matter which edge I choose at B. If you can imagine this in three-dimensional space, all of the angles between those edges and the line AB would actually be the same. So the best angle to choose would probably be the one that's going to create the easiest right triangle to work with. So let's highlight the edge BC, and we'll also connect the diagonal between A and C. Now I forgot to give you that each of the edges of this cube are 10 centimeters all the way around. So we have a few unknowns in this problem. First, I want to find this angle theta. That's the question. Find the angle between AC and the diagonal AB and any of the edges of B. So we'll call that angle theta. We know that the edge BC is 10 centimeters, and we know that this is a right triangle. We can use Pythagorean theorem to help us fill in some of the missing information. For instance, the angle, or the diagonal, AC. We'll call that x for now. I can find x by using Pythagorean theorem. But I need to draw a new right triangle. Let's draw a square that represents the base of this cube. Let's label it appropriately. So we have corner A back here, corner C here. We'll connect the two diagonals. We know that the edge, or both edges, are 10 centimeters. We know that this is a right angle up here, and we're calling this x. So using Pythagorean theorem, I can now find x. We know that x squared equals 10 squared plus 10 squared, or 100 plus 100. So x squared equals 200, therefore x equals the square root of 200. Now that I know x and the other edge of the triangle BC, I can find theta using an inverse trig function. It'll help to draw a new triangle to represent the triangle that I'm looking at. Wow, it's Let's rotate this so we're in the right orientation. And let's label it. So again, this is now A, this is point C, and this is point B. AC is the diagonal on the base plane. We just found out that the length of that side is the square root of 200. We know that this is a right angle, and we know that the length of BC is 10. And the angle that we're trying to find is theta. Since I know that tangent theta equals opposite over adjacent, I can write an equation to solve for theta. In this case, opposite is across from theta. It's the side or the diagonal AC, and we know that it is equal to the square root of 200. And the adjacent side is BC, which is equal to 10. Using the inverse tangent function, we have theta equals the inverse tangent of square root of 200 over 10. So theta is approximately 54.7 degrees. In the next example problem, I'm again given a three-dimensional shape. It's not a cube this time. But this time we're going to try to find the angle between the following line segments, which are DG and BH. So first, let's draw the line segment DG, which is a diagonal of one of the sides. We want to find the angle between this line segment and the base plane EFGH. EFGH. So the angle in question here is this angle, theta. Again, filling in some of the given information, we know that the side HG is 6 centimeters, and the side DH is 4 centimeters, and the side GF is 5 centimeters. That's the only given information we have, and for the first part, we're trying to find the angle between the line segment DG and the base plane EFGH. This is fairly straightforward, as I've already drawn a right triangle, and I know two of the sides. So this is very similar to the last problem. I can write an equation using tangent. Tangent theta equals opposite over adjacent. In this case, opposite is 4 centimeters, and adjacent is 6 centimeters. So theta is simply the inverse tangent of 4 over 6, and that approximately equals 33.69 degrees. For the second example, I need to find a projection. Because the diagonal, or the line segment that I'm looking at, is BH. So if we draw the line segment BH, let's use a different color. BH. This is a diagonal that's cutting across the center of the cube from one corner to the opposite bottom corner. It's helpful here to draw the projection. Remember, we're shining a light straight down on the wire cube, and that's going to create a projection on the line or the diagonal HF. I can complete the right triangle by drawing the edge BF. And now let's fill in some of the known information. I'm going to draw a new triangle to clarify, and again we'll rotate it. And then label it. So we have the point B, the point F and the point H. We know that at F is a right triangle, or right angle. We know the length of BF is 4 centimeters. And so far, that's really all we know. The angle that we're trying to find, we'll call it alpha, is unknown. And the other two sides of the triangle are unknown. And let's label this x. And if we can find x, then we can find the angle alpha. Again, it's helpful in this problem to draw the base rectangle, and we can label this E, F, G, and H, and this is the base plane that we're trying to find the angle from. If we draw the diagonal from H to F, and then label the known quantities, we know that HG is 6 centimeters, and GF is 5 centimeters. And that the angle G is a right angle. I can find the length of HF using Pythagorean theorem. And so this is x, and we know that x equals the square root of 6 squared, which is 36, plus 5 squared, which is 25. So the square root of 61 is my side x, the square root of 61. Again, now that I know two sides of this right triangle, I can find the missing angle. One more time I'll use tangent. The tangent of alpha equals opposite over adjacent. Opposite is 4, and the adjacent is square root of 61. Rearranging and using the inverse, we find that alpha is equal to the inverse tangent of 4 over the square root of 61. And plugging that into our calculator, we get that alpha is approximately 27.12 degrees.